and other type of loads, temperature loads and other things. But in the particularly in beams, the loads are going to act perpendicular to the length of the beam. The length of the beam is so large when compared to the cross-sectional sizes, so it is considered as a straight beam. We call it as a straight beam. See, this figure shows you a long beam supported with the two supports, and these beams are supporting various types of transverse loads. The first type of load you can call it as distributed load. See, this distribution is not uniform in this figure, but when the arrow's height is same, that is that from here to here, if the distribution is equal, then we call it as uniformly distributed load. And in the similar manner, if you have, for example, you look here, if I show this load in this direction, this is called as uniformly distributed load. Suppose if it is varying from 0 to some height, some particular value, so then it is called as uniformly varying load. These are UDL and UVL, we call it, a uniformly distributed load, uniformly varying load, UVL and UDL. Another type of load which is acting at a particular point is called as the point load. Where PM is the point load which is acting at a particular point M. And if you look at this point here, the type of the load applied is the moment. We have applied directly a moment of MK at the point K. So these are the three varieties of loads which can expected to come on a beam. The beam need not have to contain all these three loads. It can contain any of the loads, and any combination of the loads can be applied simultaneously on that. So if you look at that, all the directions, whichever I have shown, see all the arrows are pointing outward, here also it is pointing outward, it is in the anti-clockwise direction. So all these three are considered as the positive signs. When they are acting in these respective directions, they are considered as positive signs. So therefore, if you look at this, these are negative signs because they are acting towards the beam. So these two are considered as negative, those are all positive. See, when because of this upward load, the beam is expected to bend like this. This is called as the deflection curve, where V is the deflection of the centroidal axis. It has been, you can say, deflected. So at a distance of x, if you know, this is the deflection at a distance of x. We need to find out. And at this particular point, to the x-axis, if you draw a tangent, the angle made by the x-axis and the tangent is called slope or rotation, what we call it. Generally, at this particular point, it is shown as the V is the deflection, and V dash is what is called as the rotation, or you can say the slope at this point. See, in the case of one-dimensional element like 1, 2, it is having two nodes only. You found that Q1 and Q2 are called as nodal displacements. In the case of truss, there also you got 1, 2, but you have got 4 degrees of freedom. There also these were the 4 displacements, Q1, Q2, Q3 and Q4. So in both the cases, we find that these are only the displacements in the either x direction or y direction. Whereas in the case of a beam, we model it as again a two-noded element only, but the degrees of freedom associated with each node is, one is the transverse deflection and another is the rotation, you can say. This is called the transverse deflection. There is a deflection in the vertical direction which we call it as V, and this rotation or slope, what we call it, it is represented by theta or V dash, or some other name can be given, that is dV by dx at 1. Since you are taking at node 1, it can be taken like this. So therefore, the type of the degrees of freedom in beam elements they are called as, you can say, one is transverse deflection and another is rotation or the slope, what we call it. So now if you look at this another figure here, we have considered a small length of the beam. The beam length is considerably large, but when we consider a small length, this is called as the centroidal axis. If you look at the side view, this is the cross section where centroid is acting at the point G, and this is also called as neutral axis. The speciality of the straight beam is that the neutral axis always passes through the centroid, and always you know that bending stress always varies linearly, and it is maximum at the extreme fiber, and bending stress is always 0 at the neutral axis. So one side it is compressive, another side it is tension. So look at the bending moment positive, and the shear force V, capital V represents the shear force. Here I have considered a small elemental length of dx, and in this cross section I have considered a small strip of length of cross sectional area dA. It is located at a distance y from the neutral axis. This is what I have considered. and for my future calculations, these are very much needed there. Now let us consider the other parameters from the potential energy approach. Let us say potential energy approach. See, before that, you know, bending stress is always given by M by I into Y, where M is the bending moment applied to the beam, I is the moment of inertia of the cross section about x-axis or y-axis, and Y is the distance of the fiber under consideration from the neutral axis. And according to Hooke's law, you know that Young's modulus is given by stress upon strain. So therefore, strain is given by epsilon is equal to sigma upon E, and if you substitute this, it is M by IE into Y. This is what we can find out for the linear strain. This is the linear stress and linear strain, we are getting that. So we are also knowing that there is a relation called M into EI into d square V by dx square. This is the equation for deflection, we are using this. So obviously if I want to find out d square V upon dx square, it is going to be straight away M by EI. This is the thing we are making use of this expression in our future these things. Now let us consider the elemental volume, whatever it is shown here, elemental volume. Now let us write the strain energy for this. The strain energy in an element of length dx, in an element of length dx and area dA. What is this? Tell me. UE is always given by half over area sigma into epsilon into dV, and you know that it is given by, this is of course over the volume, and when you convert this into over the area, this is epsilon into dA into dx. The volume dV for this, since both areas and the length are elemental in nature, so we write the elemental volume as the product of dA into dx. Now let us substitute this. What is this? You tell me what is this thing we'll substitute. Half area. The sigma is M by I into Y, and epsilon is M by IE into Y into dA into dx. I will write like this. So I will rearrange this. What I will get, tell me. If I take this, this is going to be half M square upon I square into E into, I will shift this integration sign here, and Y square dA I will write here, and all this I will multiply by dx here, like this. From the applied mechanics, you are already knowing that integration of Y square into dA, moment of area, is nothing but the moment of inertia I only. So therefore, when I substitute here, what I will get is, you can definitely come back to this, because this expression is already over. So I can directly use this derivation part at this point. Yes. See this, I can modify it as UE. This is the elemental level. Of course, UE is equal to half M square into IE now, because one I gets cancelled with this. If I substitute this I, this as our I, this I get cancelled into dx. So here what I will do is, I will take this M square, I will multiply and divide by EI. So therefore, I will multiply and divide by EI, and this is what I will get. So therefore, if I take this, this is nothing but half M upon EI whole square into EI into dx. That is, I am multiplying, dividing by EI, and if I use this relation, M by EI is nothing but, it is going to be half EI into d square y by dx square, d square V upon dx square whole square into dx. This is exactly what you will get for the strain energy for this element. Now therefore, in case if I want the total strain energy, total strain energy in the beam is given by the entire beam. Beam is given by, I need to find out the integration EI into d square V by dx square whole square into dx. This will give you what you call it as the total strain energy. Please remember, this is called as total strain energy. But you are already knowing from the first units that the total potential energy is nothing but the sum of the strain energy and the work potential. So now let us consider that. See, for example, our total potential energy is equal to phi. It is given by strain energy, which is U, plus work potential, which is called as V. And the work potential is always due to three types of loads, which I have shown. One is the distributed load, another is the point load, and another is the moment which is applied. So therefore, I will write in detail here, phi is equal to half epsilon EI into d square V by dx square whole square into dx over the length L minus, you can take the 0 to L also, minus the, what you can say, the work potential due to the distributed load is given by this, and due to the point load PM into VM, corresponding deflection at that point, and the summation of all the moments Mk into Vk dash. So this is going to be the total, you can say, potential energy of the entire beam. So from this I can find out, this is always needed for finding the element stiffness matrix. For deriving the element stiffness matrix, later on I am using this expression and I am trying to convert this from Cartesian coordinate to the natural coordinate zeta, and then I will derive the element stiffness matrix for a beam. Now come on, let us now go for how to make the finite element formulation of a given beam. Okay, so let us take one small length of the beam, so that is one complete beam we will consider. Then we will start discretizing that, and then we will see how exactly it. FE formulation we will write finite element formulation. Okay, like this I will take now. See here, for example, I will consider a beam of considerable length here. I will divide this into 4 parts like this, and I will put 5 nodes here, here, and here, and here. These are 1, 2, 3, 4, and 5 nodes are there, and there are 4 elements, 1, 2, 3, and 4 elements are there. And as I have already told you, each node is subjected to what you call it as, you can say, Q1, Q2. One is the translation and another is the rotation. See, always remember this direction what I am using are the positive direction. Upward is positive and anti-clockwise is considered as positive. So therefore, there are everywhere odd numbers Q1, Q3, Q5, they all represent transverse deflection, like for example Q7 and Q9. These are all transverse deflection, whereas these rotations are all even numbers, and these are representing 5 rotations and 5 transverse deflections. So totally there are 10 degrees of freedom are associated with this. So if I show you Q for this particular beam, it is going to be a column matrix of 10 by 1, because there are Q1, Q2, Q3, Q4, and Q5, Q6, Q7, Q8, Q9, and Q10. These are going to be the, you can say, total, you can say, degrees of freedom. Out of Q1, Q3, Q5, Q7, and Q9. These are nothing but the transverse deflections. These are all vertical deflections only. Whereas all the even numbers like Q2, Q4, Q6, Q8 and Q10 are all the rotations or slopes. Rotations or they are also called as slopes. Please remember the unit of this is meter. This is always in radians. The unit of slopes is always in radians. This is a very important point what you have to remember here. When it comes to the force, what you need to be applied. For example, you have a force here. Always there are two forces. You can call it as F1. Suppose if it is a node 1 and 2, F1 and M1 are going to be the loads which are applied here, and F2, M2 are going to be the moments and force which are applied at this point. So therefore, for example, if I say what is the force vector here, it consists of one force, one moment, one force, one moment at the other two nodes like this. And remember, the unit of this is going to be Newton, unit of this is going to be Newton meter, Newton and Newton meter. So that's why individual, you can say, values have got their own units. First one is Newton for being a force, another is a moment. So therefore, it is to be written as Newton moment like that. So naturally, when I separate this, for example, if I want to write the element connectivity, see, first let us take only one element. For example, if I take one element which is called as element E, then the number may be anything, element number 1 or 2, 3, 4, whatever you give the number. There are two local nodes, 1, 2, and always we take this degrees of freedom associated with as small q1, small q2, small q3 and small q4. Please remember, element nodal vector is always going to be q1, q2, q3 and q4 transpose. Out of this q1 and q3 are the elemental transverse deflections. q2 and q4 are the elemental rotations or slopes. So therefore, there are totally always remember 4 degrees of freedom are associated with every element. Whereas when you look at this, the size of this depends upon the total number of nodes and the into 2, that is total number of degrees of freedom associated with that. That is going to be the global nodal, you can say, displacement vector. This is called as the global nodal displacement vector, and this is the elemental level experiment. See, some of the, we can say, other names which are given as, this is given as V1, this is as given as V1 dash, and sometimes they will give it as theta 1 also. This always will be given as V2, this is given as V2 dash or theta 2. These are all one another same. You can consider V2 dash is nothing but dV by dx at node 2, and V1 dash, it can also be written as, this V1 dash can be written as dV by dx rotation at node 1, and V2 dash can be written as dV by dx at node 2. This can be used for writing the details of that. So therefore, if I want to connect the mapping, like for example, if you look at this figure, there are local nodes are 1 and 2. Everything has got 1, 2, 1, 2, 1, 2, 1, 2 like that. These are the local node numbers. But when these are local node numbers, you can say. These are local node numbers. And there are totally 1, 2, 3, 4 elements are there. In your case, it is 4 elements. So the connectivity says 1 and 2, 2 and 3 for the second element, 3 and 4 for the third element, and 4 and 5 for the fifth element, that is fourth element. This is called as global nodal numbers, node numbers or nodal numbers, you can say. This is what we call it as the element connectivity table, and from this one can find out all these details now like that. Okay. Now, another very interesting point what I would like to tell you here is about the interpolation. That is what in the previous classes we have seen for one-dimensional elements with 2 node, 3 node, and we have also considered 2-dimensional truss elements and all that we have considered. There we defined what are called as the shape functions, and these shape functions were linear in nature or in quadratic in nature, and that's why they are all called as Lagrangian shape functions. But as far as beam is concerned, since the degrees of freedom associated with every node in a beam are not in the form of displacements. Here it has to take care of one transverse deflection as well as rotation or slope. So to take into account this, we are defining a separate type of shape function called as Hermite shape functions. Please remember, these Hermite shape functions are basically defined for beams only, for taking care of what you call it as the, you can say, transverse deflection and the rotation of this. Generally, this written, there are totally 4, you can say, shape functions. This is given by AI plus BI zeta plus CI zeta square plus DI zeta cube. See, if you take the beam element here in the natural coordinate system, this is the node 1 and node 2, and this is going to be zeta equal to -1, zeta equal to +1, and the midpoint is just shown as zeta equal to 0. But there is no node at the midpoint. 1 and 2 are the end nodes, and the values of zeta varies from -1 to +1. So therefore, the shape functions are always defined with respect to zeta is equal to -1 and zeta is equal to +1. So for example, if this is the case, we have to find out, for example, if you want h, here I varies from 1, 2, 3, 4, because I need 4 shape functions, 4 Hermitian shape function, H1, H2, H3, H4. So the moment you put H1, for example, H1 if I put, it is going to be A1 plus P1 zeta plus C1 zeta square plus D1 zeta cube, like this. Similarly, if you write H2 of zeta, A2 plus B2 zeta and all that, you will get it like that, H3, H4 and all that you will get. Now, these shape functions are governed by certain relations. See, for example, if I find out the values of zeta equal to -1, that is node 1, you can say this I will write it as node 1 and node 2. We will write it as node 1 and 2. This is at zeta equal to -1 and zeta equal to +1. As you can see there, the values of zeta is this. Now, I want to know the values of the shape functions here now and corresponding slope. For example, if I write H1 and H1 dash is the slope at this, that is, this H1 dash refers to dH1 upon d zeta. When you differentiate this H1 with respect to d zeta, this is called as H1 dash. Similarly, you will get H2, H2 dash, H3 dash, and if you have H4, you will have H4 dash. So I can just close this. These are the different values which we are going to find out. Now if you look at the values, they are supposed to be 1, 0, 0, 1 here, 1, 0, 0, 1 here, and the remaining all these values are going to be zeros here. So here also it is 0, 0, 0, 0. So the meaning of this is going to match a certain specific, you can say, requirement for finding the shape functions of that. First, let me show you how exactly the shape function varies. See, let me show you in the form of the variation of these shape functions along the length of the element. Shape functions, for example, as I told you, H1, H2, H3, H4. These are the 4 shape functions which will be defined now, and their variation along the length of the element I am going to show you. For example, let me show first one, that is, this is our, what you can say, zeta coordinate, and this is our node 1 and node 2. As I told you, this is always node equal to zeta equal to +1 and -1, and this is of course zeta is equal to 0. Here, what is happening here is, the variation is something like this, it is coming here now. This indicates that this is of course the variation of the first shape function H1, and H1 is always 1 at zeta equal to -1, that you can see here. H1 is 1 at zeta equal to -1, and it is 0 here. Whereas the slope H1 dash is 0 at both these points. So you can see here, here and here, the slope is 0 at these 2 points. This is how the variation of the first shape function is considered. Now suppose if I want to consider the second shape function, You see here, if you take, you can say H2. H2, when you look at this is the shape we are going to get the H2. That means if I draw 1 and 2 here, again this is zeta equal to -1, zeta equal to +1 if I take, and this is zeta equal to 0 if I take. If you see here, the slope at node 1 is not 0, it is 1. Whereas at node 2, the slope is 0. That is H2 dash is 1 at node 1 and it is 0 at node 2. See, 1 and 0. This is node 1, this is node 2. So this variation is very clearly seen on this particular graph. Similarly, let us go for what you call it as the H3. This is again zeta. And here, this is going to be like this. Here it will be like this. This H3 is equal to 1 at node 1. See here, this is again going to be zeta equal to -1, zeta equal to 0, zeta equal to +1, and this is your S3, which is variation of the S3. And you can see there, S3 dash is 0 at both the points. See, this is a H3 dash. It means slope is 0 at both the points, whereas S3 is 1 at zeta is equal to +1. You can see there. Zeta equal to +1, S3 is 1, whereas it is 0 at node 1, whereas slope S3 dash is 0 at both the ends. This is how this figure matches. And coming to the last, you can see here, what is happening here is 1 and 2, and this is zeta equal to -1, zeta equal to +1. We find that the slope is existing, that is slope at node 2 is 1, whereas the slope at node 1 is 0, that is H4. If you look at this, this is our H4. This is the variation of H4. If you look at this H4 is 0, 0 at node 1 and node 2, whereas H4 dash, that is slope, is 0 at node 1 and it is 1 at zeta equal to +1, that is node 2. This is what you can see. So these are the 4 shape functions by which we are required to now find out the individual values of these H1, H2, H3 and all that. For example, now let us find out what is the H1. Let us take H1, we will find out, H1 zeta we will find out. See, H1 zeta will be A1 plus B1 zeta plus C1 zeta square T1 zeta cube. Now I have already told you, this is what we want to take. This is what we call it as the H1 dash. This will be obviously B1, A1 being a constant, it will be 0. B1 plus 2C1 zeta plus 3D1 zeta square. See, these are the two important equations for all the 4 shape functions. Now we know that by putting these values of zeta equal to +1 and zeta equal to -1, see, for example, zeta equal to +1, I will put it here. Now what is this? H1 is going to be zeta equal to +1, it is 0. So therefore, it is going to be 0 equal to B1 plus, sorry, not B1, H1, no, this is A1 plus B1, because zeta equal to +1 you are putting, plus C1 plus D1. This is your equation number 1, you can call it. When you put the value of zeta equal to -1 in this equation, what will happen? When you put zeta equal to -1, H1 is 1. So therefore, this is 1. A1 minus B1 plus C1 minus D1. Because when I put -1 cube, it is going to be -1 only. So this is what we will get. Similarly, let us take H1 dash. That is zeta equal to +1. What is this? H1 dash. You see here, H1 dash is going to be 0 at these two. And zeta equal to -1 also, it is 0. That is H1 dash at zeta equal to +1 and -1. Both way it is 0. So this will be B1 plus 2C1 plus 3D1. This will be B1 minus 2C1 plus 3D1. So these are the 4 linear equations I have to find out the 4 unknown constants. If I evaluate these 4, if I go on finding the combination of these equations, and if I start evaluating these, I will be getting the corresponding values of these shape functions. For example, let us take equation number, which one will take 3 and 4. We will take now 3 and 4. Let us see. What are these 3 and 4? You see here. If you take the minus of this, for example, minus, 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 and this if you take plus, this cancels, this cancels, this will be equal to 4C1. See, from 3 and 4, 4C1 is equal to 0 only we are getting, because both sides it is 0. So this indicates that the value of C1 is 0. That means one of the constant is got eliminated from our equation now. Now let us come to next combination of equations to find out the other remaining 3, like B1 and B1, A1, B1 and D1. We need to find out. So by chance, if I take let us say equation 1 and 2, equation 1 and 2, if I take, what will happen, tell me? Look at that. 0 equal to A1 plus B1. C1 has already gone, it is 0, so I will write this. 1 equal to A1 minus B1 minus D1. This is what I will get that. So if I take this here now, what will happen? This and this get cancels. 2A1 equal to 1 or A1 equal to half. So this is the second constant you have got now. You have got C1 equal to 0, A1 equal to half you have got. In the similar way, if you take equation number 1 and 4, what will happen, tell me? 1 and 4, what will come? 0 equal to A1 plus B1 plus D1. I will totally eliminate what you can say C1. 4, what it says? 0 equal to B1 minus 2C1. C1 has gone. B1 plus 3D1. I got it. This. Okay, fine. So here, if I change this, what will happen? Yes. This will be equal to 2 and 4. I think we can take 2 and 4 instead of 1 and 2. 2 and 4 will take. That will be better. 1 equal to A1 minus B1 C1 minus D1. 0 equal to B1 minus 2 C1. Yeah, minus B1 plus B1 minus 2 C1 plus 3 D1. Okay, fine. If I take like this, what will happen? Anyway, this is already gone. This is not there. So this is also gone. So this will be 2 D1. 1 is equal to half plus 2 D1. This is because already you have calculated it. So therefore this will be equal to 1 minus half is equal to 2 D1, and D1 will become, this will be half. Naturally this is half. So this half, if I divide it by this, will give you 1 by 4. So therefore we got the next D1 as 1 by 4, and last if you substitute this, all this, you will get minus 3 by 4, you will get it for B1. So this is how, by using these combinations of these equations, now you can evaluate all these 4 constants. So that now I can rewrite my shape function now, H1, completely I can write now that. What is that shape function I can write, you tell me? Look at this. H1 of zeta is equal to half, is there A1, plus B1. B1 is minus 3 by 4. B1, this is just we have found out. C1 anyway it is 0, plus D1, it is 1 by 4. So therefore, what I will do is this 3 by 4 zeta, zeta square has gone because 0 into zeta square minus or plus 1 by 4 zeta cube. This is what you are going to get that. Suppose if I remove 1 by 4 out of this, it is 1 by 4 will come 2, because it is 1 into 2, this will be there, minus 3 zeta plus zeta cube. This is going to be what is called as H1 of zeta. Maybe if you want to add some parameters to this, You can modify this as 1 plus 1 upon 4, 1 minus zeta whole square into 2 plus zeta. This way also you can write it for your convenience. So this is exactly what we call it as h1 of zeta. That is first Hermitian shape function for the beam element. In the similar way, we can go for, I don't want to go for all of them, but just to show you. For example, h2 of zeta, if I want to write, it is a2 plus b2 zeta plus c2 zeta square plus c3 zeta cube. This is what you will get. And if you want h2 dash of zeta, that is b2 plus 2c2 zeta plus 3 zeta square. This is your equation number 1, this is equation number 2. And once again, not this equation, of course you can now write 4 equations by substituting zeta equal to plus 1, zeta equal to minus 1, zeta equal to plus 1, zeta equal to minus 1. First you put these two in this equation, that is h2 of zeta. Look here, h2 of zeta at zeta equal to 1. Where is that? This is 0. Okay, this is 0. So therefore, this is 0 is equal to a2 plus b2 plus c2 plus d2. Okay, this is going to be d2. This is will be there. And here this is of course d2. And when you put here h2 of zeta, again it is 0. You see here at zeta equal to minus 1, it is again 0. That is it is 0 at both the points. So therefore, once again I will write it. So this will come b2 plus 2c2, okay, minus 2c2 plus 3d2. This is what you will get. You can call them as equation number 1 and 2. Okay. So this will be a2 minus b2 plus c2 minus d2. This is for the h2 of this. So here next comes h2 dash at zeta equal to 1. See here h2 dash at zeta equal to plus 1, it is again 0. So therefore it is 0 is equal to, yes, b2 plus 2c2 plus 3d2. Whereas h2 dash at zeta equal to minus 1, it is 1. So therefore b2 minus 2c2 plus 3d2. You get this as fourth equation. So you have once again have got 4 sets of equations, and please solve them by using different combinations of equations. In the similar manner, if you do it, I will just show you. If you use equation 3 and 4, if you use this equation 3 and 4, C2 is coming to be minus 1 by 4. If you use equation 1 and 2, you will get A2 equal to 1 by 4. And if you use the equation 2 and 3, you will get a D2 equal to 1 by 4, B2 equal to minus 1 by 4. You will get all this. So obviously, this will give you the complete picture about the H2. So let us see what is that H2 now. A2 is going to be 1 by 4 plus B2 minus 1 by 4 zeta. C2 is again 1 by 4 zeta square plus 1 by 4 zeta cube. See here all are going to be 1 by 4. So therefore I will take it as 1 minus zeta square plus zeta cube. So this can be written as 1 minus zeta whole square 2 minus zeta. This way you can write like this. This can be written as zeta plus 1. Here, please look at this. This is the second Hermitian shape function in terms of this. Okay. So like that, I can write the 2 more. I will not derive everything now. I will directly write down what are the values of S3 and H4. For example, S3 of zeta will come half 2 plus 3 zeta minus zeta cube. This is also equal to 1 by 4 1 plus zeta whole square 2 minus zeta. You will get that. Similarly, if you want h4 of zeta, it is 1 by 4 into bracket minus 1 minus zeta plus zeta square plus zeta cube. This is what you will get. And if you really write this in the form here, yes, this is going to be what is called as the 4 shape functions. See what is the use of these 4 shape functions? Like for example, I'll just tell you, if you take, this is your 1 and 2, in the case of what you can say, one dimensional 2 noded bar element, what we have seen? We had seen that the displacement of this was Q1 and the displacement of this node was EDC. Suppose if I want any point where if I simply specify the value of zeta, how to find out the displacement of that particular point, unknown point. So naturally we had defined 2 shape functions there. Then we call it as n1 and n2 as 1 minus zeta and 1 minus zeta by 2 and 1 plus zeta by 2. And then by knowing these nodal displacements Q1 and Q2, what we had found out was n1 Q1 plus n2 Q2. This is exactly we had found out. To find out the unknown nodal displacement at any point of zeta, you specify the zeta minus 1 to plus 1, you take any value. It may be varying from minus 0.8, minus 0.3 or something like that, or beyond 0, that is 0.1, 0.25, 0.7, up to plus 1. You can put any value of zeta. By using this relation, I could have found out the, you can say, displacement at a given point. In the similar manner, for example, as I told you, if I want the deflection at a given point for a beam, now look here, this is our beam, this is 1 and 2, the beam is getting deflected here, this is Q1 and this is going to be Q2 and this is going to be Q3 and this is going to be Q4. And if you know this, this is our zeta. Suppose if I want a value of zeta, what is my deflection? V in terms of this. So if I want this, then I can write that V at a given zeta is given by H1 Q1 plus H2 Q2 plus H3 Q3 plus H4 Q4. This is what you can find out from this displacements here now, like this. This can also be written as you know, H1 Q1 and this H2 is there, obviously there. This is nothing but Q2 is what? dV by dx at 1 and H3. Of course, this is not deflection at x, it is, please remember. This is the given at a given value of x. If you want to find out dV by dx at 2 plus Q4. So these are the values which are to be found out. So therefore, if I want, I can rewrite this as H1, H2, H3, H4 and this one as Q1, because it is a column matrix, Q3, Q4, what you will get, and this is equal to HQ. This is the, you can say, form which we are going to get this. This is the format in which we are going to get the, you can say, deflection of the beam in terms of x coordinate, please remember, and still we have to convert that from x coordinate to zeta coordinate, the natural coordinate. Okay, now let us quickly go through this. Let us go for the coordinate transformation. the coordinate transformation by the relationship x is given by n1 x1 plus n2 x2, where for one dimensional you already know that it is 1 minus zeta by 2 x 1 plus zeta by 2 x2. This is what you are already knowing this. If you simplify this, it is x1 plus x2 upon 2 plus x2 minus x1 upon 2 into zeta. This is what you will get. This is x. And you are already knowing that x2 minus x1, physically it represents the length of the element, because from x2 x2 minus x1 will give the length of the element. So therefore, if you take the differentiation of this, this is going to be LE by 2 d zeta. Or if you want d zeta, it is 2 by LE into dx. Either of the one you can take and form the relationship between these two. This is what we have studied in our past classes now. Yeah. Now, as I just now told you, V of zeta, since it is going to be in the form of zeta, H1 V1 plus H2, please remember this is going to be with respect to these zeta, in terms of zeta I am taking, S3 V2 plus S3 V3 plus what you can say H4 d V upon d zeta at 2. This is what we need to find out. This is at node 1 and node 1, node 2, node 2. This is going to be at node 1 and node 2. Now we need to find out how to relate dV by dx as well as dV by d zeta. Now let us go by dV by d zeta. Let us use the chain rule dV by dx into dx by d zeta. We'll use this. We'll try to find out this dV by d zeta. And you are already knowing dx by d zeta from this relation. What is this dx by d zeta? This will give you dx by d zeta, will give you LE by 2, it will give you the length of the element, half of that. So therefore, if I take this, it is going to be LE by 2 dV by dx. Or if I want dV by dx, it is LE by 2 dV by d zeta. This is what you will get that. Okay. So therefore, once we know this, this can be found out. This is what we would find out. For example, if we want at node 1, it is going to be, I have already told you, this is Q1 and Q2. This is Q3 and this is Q4. Please remember Q3, Q2 and Q4 are nothing but dV by dx at node 1 and Q4 is dV by dx at node 2. This is like this. This is with respect to the x coordinate. Always remember, slope is always defined with respect to x coordinate. So therefore, if I want to write the similar value here, since I know this is LE by 2 dV upon d zeta at 1, and this is also equal to LE by 2 dV by d zeta at node 2. This is what will be knowing the relation between this Q1 and Q2. That is what you have to remember, Q2 and Q4. So, from these relations, what you will get to tell me? If I want dV by d zeta at 1, it is nothing but 2 by LE, is it 2 by LE or LE by 2? That exactly you have to check this. Okay, come on. Let us quickly look into this. Let's go to the chain rule. Where is the chain rule? Yes, this is our chain rule. See, according to chain rule, yes, just tell me, what is the chain rule here? dV by dx is equal to dV by dx into dx by d zeta. What is dx by d zeta? Now let us look into that. Dx is equal to LE by 2 by LE, it is exactly. See here, it is nothing but, yes, it is LE by 2, dx by d zeta is equal to, yes, this is LE by 2. And if I put this into this chain equation, what will happen? dV by dx into dV by dx. This is equal to LE dV by d zeta. Correct. It is dx by, no, dV by dx. Correct. Exactly. This is what you will get. Correct. Exactly. But since I have already told you, Q2 is given by dV by dx at 1 and Q4 is given by dV by dx at 2. Correct? So therefore, if I want the value of dV by dx, d zeta at 1, it is going to be LE by 2 into dV by dx at 1, which is nothing but LE by 2 into Q2, because this is equal to this. Please remember, that is equal to this. Similarly, if I want dV by d zeta of 2, if I want, it is LE of 2 dV upon dx at 2, which is LE upon 2 what? Q4. Exactly. This is going to be Q4. So therefore, if I take this equation for V, how exactly it is going to be written? Tell me. Substitute that into the equation for the deflection. See, ultimately, this is very, very important. There is deflection at a given point. So V of zeta, if I want, it is H1, Q1, I will write. Now H2, okay, these are all in terms of zeta. So now dV by d zeta at 1, when I want, I need to take this as LE by 2, Q2. Similarly, H3 into Q3 will be there, but when it comes to H4, it is LE by 2, H4 into Q4. This is exactly what you are going to get this. So that means in the slope, LE by 2 is going to getting added. So therefore, if you write this, H1, LE by 2, H2, S3, LE by 2, H4, and if you write this as Q1, Q2, Q3 and Q4, if you write now, this is nothing but H into Q. Please remember, this is the deflection equation. So that means if you want to find out the deflection in an element, for example, if this is your element 1 and 2, you have subjected to some load, like let us say some UDL has been put on this. So you will be converting this UDL, always please remember this, all this UDL has to be converted into equivalent nodal loads. We call it as this UDL is converted into equivalent nodal loads. Nodal loads are in the form of one force and one moment. F1 and M1 I am putting, and F2 and M2 I am converting this. What are the values of this? I will tell you later on. But when you find out these loads, there is going to be deflection. So if you want to find out any deflection, which we call it as V of zeta, one has to definitely tell the value of zeta. Where exactly you want to find out the deflection? Suppose sometimes if you are asked to find out the deflection at the midpoint of the element, then here it is. Like this particular value of zeta is obviously 0. So if you are asked to find out the deflection at the midpoint of the element, simply you substitute zeta equal to 0 in all these equations. You know that h1, h2, h3, h4 all are functions of zeta. That is, I have already showed you 2 minus 3 zeta plus zeta cube and all that, 1/4 and all that. All are going to be, I can say, functions of zeta, and by substituting that, I can get directly the values of this. So today we have come to a very, very important conclusion, that is how to relate the Cartesian coordinate values to the natural coordinates, and then we found out the relation to find out the deflection of a beam at a given location. So therefore, in the today's these things we have successfully noted down that how to find out the values of the shape functions and all other things since we have seen that. Okay, so our next objective is, once you have derived, for example, I will just show you V of zeta is equal to h q, you have written, and this is nothing but h1 q1, or you can write it as h1 Le by 2 h2 h3 Le by 2 h4 into q. Why I am writing is this, we need to find out. For example, if I want to write all these shape functions, this is, what is this? 1 by 4 2 minus 3 zeta plus zeta cube. This is your first one. Le upon 2. Again, this is written as 1 by 4. What are the values we had found out for all the 4 shape functions? Let us see quickly what all we had found out in our derivation. This was taken as a minus 1. Okay, 1 minus zeta square plus zeta cube into Le by 2. S3 was 1 by 4, 2 plus 3 zeta minus zeta cube. And once it comes to Le by 2 into 1 by 4 minus 1 minus zeta plus zeta square plus zeta cube and into this cube. Why I am telling is, since our strain energy consists of d square V by dx square and further square of that, so obviously we need to take this expression and we have to go on differentiating with respect to this, because once we know this dV by dx, okay, if you write the strain energy equation, what is that we have written? Half 0 to L EI d square V upon dx square whole square into dx. Now this I need to substitute this as in terms of this, I have to bring it, because finally this, all this x term need to be converted into zeta term. So once we get that, then it is easy for us to find out the element stiffness matrix for beam element. So that I think we'll take it tomorrow. We'll discuss in detail about how to find out the element stiffness matrix for a beam, and then we'll take up a number of varieties of problems, how to form the global load vector and all the details.